Hello, this is Hideo Kobayashi. Kobayashi YouTube University of Science and Technology, 11th delivery. Today, I'm going to talk about the vibration, especially in how to measure natural frequencies of objects. So as for the vibration content, and today number 1, how to measure natural frequencies of objects. My name is Hideo Kobayashi. I'm a part-time lecturer at Graduate School of Nagoya University. This broadcasting is from Odoro City, Kanagawa Prefecture, Japan, to the world. Okay, I'm going to the next slide. First of all, let me introduce my book. I wrote this book in 2019. This book is published by Nikkan Kogyo Shinbunsha. This book is written in Japanese. So the title of this book is written as follows. In Japanese, 機械設計者のための振動騒音対策技術. This is for mechanical and designers, vibration and noise countermeasures. Okay. If you're interested in vibration technologies, and if you can read Japanese professional books on vibration and noise, I'd like you to refer to this book. This book is not for students. This book is for practical engineers. Okay, let me go to the next slide. So from here, I wrote the theory, how to measure natural frequencies of objects. So in accordance with this theory, the measurement using FFT, Fourier Transform analyzer, is performed. So from the beginning, let's think Newton's equation of motion in S-dot. S-dot means single degree of freedom. So the freedom is just 1. This is usually called S-dot to make it easy. Newton's equation of motion in S-dot is expressed by the equation 1. This one. This is a mass. This is about mass motion. Okay. This is about damping. This is about stiffness. And this FT expresses, it's written here, a forced external force. Okay. For example, force by motor movement or engine movement or something like that. Vibrations caused by motors, engines, etc. inside machines and equipment become forced external forces. When applying Laplace transform to the equation 1, to this one. So this equation is written in the parameter of time. Okay, so this t is t, time. It's transformed to s by doing Laplace transform. Okay, this equation is given by the Laplace transform of the equation 1, okay? Okay, it's easy to do Laplace transform like this. So the differentiation by time once becomes s. This is x is the distance. This x is differentiated by time twice. So once is it just becomes s, and the twice becomes s squared. Okay, so c times this one becomes dx dt becomes s. Okay, k x just k, and x distance becomes xs. Ft becomes fs. Okay, then j omega is substituted to s to know frequency analysis. Then this formula 2 becomes this one by this substitution. Okay, this f is input. This x equals output. So like this, we make fraction output over input. Okay, this expresses the characteristics of the object. Okay, so input is, as I explained now, f j omega. Output is x j omega. So this one, this fraction becomes this one from the equation 3. Okay, this is called okay, to express this one, we use hj omega or f. Omega equals ni pi f. So this hj omega is written hf. So this is called frequency response function. Frequency response function. But it's long to say. So we usually call this one F or F, F or F. Okay, this stands for frequency response function. Okay, I go to next slide. So according to the equation 4, we calculate F or F. Then this one becomes like this. This is a real part. This is the imaginary part. Okay. Then using this real part and imaginary part, we can make the gratitude of hj omega. So this is usually called gain. Gain, this one, gain. Gain of FRF becomes like this one by the calculation. Then finally, we get this one for the gain, F or F. Here we use theta. Theta means damping ratio. This one, theta, C over CC. CC, this small c means critical. So CC means critical damping coefficient. Okay. This omega is angular frequency. Okay. This omega n means angular frequency at natural frequency. So the gain of F becomes this one, the equation 7. Okay? So equation 7 is partially differentiated. And to know the maximum value of the gain. Okay? By doing this one, okay, the gain, the frequency response function, F for F, becomes this one, okay? And here, next slide, okay, here. The phase of the frequency response function is given by the formula 12, and this one. This is the phase of the F for F. Okay, from equation 11, this one, gain, and from the equation 12, this one, phase, we can write each figure like this. So gain, so vertical axis means gain, okay? Vertical axis here, the lower figure becomes phase, okay? So the gain becomes like this one. If theta is small, sorry, this is written in Japanese. This means small in English. This is also written in Japanese. This means big, okay, in English, okay. So blue curve shows in case of theta is small. In this case, like this. But if theta is becoming bigger, for example, in this case, the brown curve, okay? So as for the maximum value of the frequency response function, okay, about omega by omega n is almost equal to 1. Then the maximum value of a gain of F or F is given like this. But in the value of the damping ratio, theta, is becoming bigger. The peak becomes like this one, lesser than just a little bit, 1, value 1, okay, here. As for the phase of the FRF, comes like this. In case of damping ratio is small, okay? So we measure the frequency response function of the object using FFT, first Fourier Transform, okay? We go back to this slide here, okay? We measure input and output. So input is given to FFT, okay? Output is also given to FFT. Then FFT, and we make this one. That means we measure HF, frequency response function. So the frequency response function in experiment is measured by FFT, okay? So using measured F4F, okay? We get gain and phase. And in FFT, on the screen of FFT, we can write this gain figure and this phase figure. Then we see and the peak value of the gain, peak frequency, okay? Phase becomes opposite from 100 degree to 0 degree, okay? In this case, the center value, 90 degree. This curve always comes to 90 degree, like this, okay? So if at certain frequency, maximum value is given like this, then at the same frequency, the phase becomes opposite. Opposite means 180 degree to 0 degree, and usually passes. It's never failed to passes 90 degree. Okay, if this situation, this one and this one are confirmed, so this frequency recognized as natural frequency by experiment. Okay, by this procedure, we can measure frequency response function of the object. Usually, we have plural natural frequencies, not one, not single. Well, this theory is only for SDOF, single degree of freedom, but we can apply this theory to MDOF. MDOF means multi degree of freedom. If the object behaves in vibration linearly, in this case, we can use this theory for SDOF. Is used to MDOF. Okay? So usually, the object we deal machines, equipment, and so on, usually behaves linearly, but sometimes non-linearly. But usually, we can think it linear movement, linear vibration. So in that case, this theory is used. In case of nonlinear vibration, we can apply this theory, okay? But here, I just talked about the theory for linear cases, linear vibration cases. That's all for today. Thank you very much.